In this video, we're going to talk about Chapter 8, Sections A and B of Baronett's logic. Chapter 8, I consider to be the most fun of any chapter we've done so far. It's the most interesting. In this chapter, we're going to learn how to build proofs. If you've taken geometry class in high school, there's usually a unit on proving things. And what we're doing here is very much like that, except without shapes. So, first of all, what we're doing here is natural deduction. And natural deduction is a proof procedure in which you derive the conclusion of an argument through logically valid steps from a set of premises that are just given to you. And you do this by using rules of inference to prove other conclusions on the basis of those given premises. So a proof is just a sequence of steps in which each step is either one of the premises that was just given to you at the beginning, or you've proven it from those premises by using your rules of inference. The rules of inference are what you use to justify the steps of a proof. So if you think about it, like it's kind of like a game. The pieces that are given to you on the board are the premises, and you've got this goal you're trying to get to, which is to prove some conclusion. And the moves that you can make are determined by these rules of inference. So you're going to apply these rules of inference to the pieces on the board to try to get to this conclusion. And we're going to learn 8 implication rules. They're broken up into 2 sets of 4. These are the rules of inference that tell you, here's the moves that you can make. Here's what you can do with each kind of premise. So first of all, let's talk about the first set of implication rules. There's 4 of them, and they have to be applied to an entire line. So we'll start with Modus Ponens. Modus Ponens is a rule which tells you what you can do with any premises with this form. If you have a premise that is a conditional statement, if P, then Q, where P and Q can be any given statements, either simple or compound. And then you have another line which gives you P, that is the antecedent of that conditional. Then you can infer Q. You can infer that the consequent of that conditional statement is also true. So here's an example of valid applications of modus ponens. So let's say that you're given this premise. Premise 1, if R is true, then M or N is true, where M or N is the entire consequent. That is the same form as if P, then Q. Like where the Q is everything in the parentheses, that whole disjunction, if M or N. And then you're also given in premise 2, R. So the R is like the P in the argument form here. It's the antecedent of that conditional. Well, you can apply the rule modus ponens and conclude, you can infer that if these 2 premises are true, then M or N must be true. You know why? Because M or N is the consequent of that conditional premise. It's the Q, and it's standing in the place of Q, and so therefore you can conclude that it's true. Now, I think we've probably seen this before, but maybe not. When you see this line that goes across here, what that means is everything above that line are given premises, and everything below it is the conclusion. So basically, when you see that line, think, therefore, here's what follows from that as an inference. Here's another instance of applying modus ponens. You've got if P and Q, then G and not B. Now, even though that looks big and complicated, the structure here is identical to this argument form. It's if P, then Q, where everything in that first set of parentheses is the P, the antecedent. Everything in that second set of parentheses is the Q. It's the consequent. And then the second premise says P and Q. Now what is that? That's the antecedent. That's the P in that conditional. So you've got the exact same ingredients as are given to you in the premises of this argument form for modus ponens, and you can infer on that basis, therefore the consequent is true. Everything in that second set of parentheses, G and not D, that's a valid application of modus ponens. Now, here's ways that you can screw up modus ponens. And these basically involve trying to apply modus ponens to part of a premise. You can't apply the implication rules to just part of a premise. They've got to apply to the whole line. So we've got either if L then Q or R or S. And then the second premise is L, and the conclusion supposedly is Q. But here's why that doesn't work. That would be true if all that we had in line 1 was if L then Q. But that's just part of line 1. Really, the main operator for line 1 it's not a conditional statement at all. It's a disjunction. And you can't apply modus ponens on a disjunction. I mean, if that's the main operator, like a conditional statement is not the same thing as a disjunction. So that does not follow. Same thing over here. If you've got, either if L then Q or R or S in line 1, and then you've got L in line 2, and they try to conclude to R or S. Again, here's the issue here. Is line 1 a conditional statement? No, it's not. It's not a if P then Q, it's a either or. It's almost as if, I don't even know what they messed up here. What was the mistake that they were making? It's not even close. So the point is, you can apply modus ponens if one of your premises is a conditional statement and another premise is the antecedent to that conditional statement, then you can conclude to the consequent. Now, it doesn't actually matter which order the premises appear in. So, even if you had line 1 was P and line 2 was if P then Q, you could still apply modus ponens and infer therefore Q. All right, that's modus ponens. Here's a concrete example. This may help you to get it more. Here's the correct form of it. And here's the correct application. You got if P then Q. Let's say that P stands for it's raining. Let's say that Q stands for the streets are wet. So line 1, premise 1 says, if it's raining, then the streets are wet. That's the conditional. Premise 2 says, well, it is raining. The antecedent is true. So modus ponens license you to say, therefore, the consequent is true. The streets are wet. And don't get that mixed up. It's easy to get that mixed up with the fallacy, the mistake that's called affirming the consequent, okay? When you affirm the consequent, it's a mistake. And what you do there is you say, if P then Q, so far so good. But then line 2 is Q. And you try to conclude, therefore, P. That doesn't work. Look, line 2 here is the consequent. And in the correct form, the second premise, the other premise is the antecedent, and you conclude the consequent, but you can't be given the consequent and then conclude to the antecedent. This will be easier to understand with the example. So here's the fallacy. If it's raining, then the streets are wet. So far, fine. Premise 2, the streets are wet. Therefore, it's raining. But that doesn't follow. That's not necessarily true. Think of a situation, prove it to yourself. Try to imagine a situation in which it's true that if it were raining, the streets would be wet. And where it's also true that the streets are wet, but where it hasn't been raining. How could that be the case? Can you conceive of a counterexample? Yeah, maybe somebody just hosed down the streets. It's not raining. If it were raining, the streets would be wet. And it's true the streets are wet, but it's not raining and it wasn't raining. Somebody just hosed down the sidewalk. So that's why you can't make the fallacy of affirming the consequent. Next rule is Modus Tollens, which is similar to Modus Ponens, but different. So Modus Tollens starts the same way. It's got a conditional statement, if P, then Q. But then the other premise says not Q. Now, this isn't the fallacy of affirming the consequent, because it's not saying Q, it's saying not Q. In other words, it's saying if P is true, then Q is true, but Q is not true. So what do we know? What can we validly infer from that? Well, therefore, P must not be true. So you move from a conditional to the denial of the consequent to then the denial of the antecedent. Here's the valid applications. If H, then T or N. Well, it's not the case that T or N. The consequent's false. Therefore, we can conclude by Modus Tollens that therefore it's not the case that H. Or this one. If G and D, then C, but not C. Therefore, not G and D. Now, I want you to notice something important about this second example. When you conclude that the antecedent is false, that it's not the case that G and D, it's very important that you preserve those parentheses and you put the negation sign outside of the parentheses. If you were to drop those parentheses, this would, and just said not G and D, that would be totally different and totally wrong. Now, here's a misapplication, of Modus Tollens. Either if L, then Q, or R or S. Well, it's not the case that Q, therefore it's not the case that L. Again, this was an attempt to apply Modus Tollens to just part of a line. If there were no, if you just cut off line 1 after the end of the parentheses, the first parentheses, this would be valid. It would be Modus Tollens, but you can't do that. This isn't a conditional statement. Line 1 is not a conditional statement. It's a disjunction, and one of the disjuncts is a conditional statement. But you can't just like apply an implication rule to part of a line. So here's a concrete illustration. So the right way of doing Modus Tollens validly would say, if it's raining, then the streets are wet. But the streets aren't wet. Therefore, I can conclude by Modus Tollens, it must not be raining. That's the right way. Now, here's the fallacy, the way of screwing this up. Kind of parallels the fallacy of affirming the consequent. There's also a fallacy of denying the antecedent. And that's when you say, if P, then Q, not P, therefore not Q. In other words, instead of denying the consequent, you were denying the antecedent P, and then try to conclude to the denial of the consequent. So if you make this concrete, if it's raining, then the streets are wet, but it's not raining. Therefore, the streets must not be wet. That doesn't follow, folks. Can you think of a situation in which it's true that if it were raining, the streets would be wet, and where it's also true that it's not raining, but where actually the streets are wet? Sure. Again, somebody's hosing down the sidewalks, and there's water all over the streets. That is a perfectly legit possibility. So don't make the fallacy of denying the antecedent. 2 more rules here. Actually, let me stop here, and then we'll in the next video we'll cover the next 2 rules.